Hi there. Let's talk about x86-64 programs and their segments, and the purpose of the segments. Probably when you've been programming in the past, you've seen segmentation fault errors. If you've accidentally, crossed the bounds of some, appropriate memory location, if you have an array and you try to index it way outside of bounds or something, you might have seen a seg fault. Seg faults basically come from the idea that you have crossed a segment boundary. Segments used to be really, really important. They're a little bit less important now that we have virtual memory. I'll just talk a little bit about them. I'm going to be discussing this from the perspective of an assembly program, just because even in higher level languages, your languages will typically be compiled down to assembly first before they actually hit machine code and your actual executable binary. So if you're not interested in Yasm assembly, I think this could still be worth it for you to watch, because you'll be able to see the different segments and just kind of get a better understanding of what they are. Okay, so I'm going to actually write a very quick program in assembly. It's not going to really do anything. I just want you to see the segments that are involved. So for starters, let's just pretend that I'm writing an assembly program here. We'll say that semicolons are comments. This is a comment, just so you know what I'm about to type. Perhaps actually this is not the best editor. I don't know why I pulled this up. Let me get Genie here. It's a little bit better. Genie. There we go. Maybe I'll save it somewhere. I'll say segments, assembly, and then now the comment gets highlighted. Okay. So in Yasm assembly, we denote various segments by using the section keywords. So we'll say section and then dot something, indicating the type of segment that we're defining. So section text, and then up here we'll have another one, section.bss. And if you already program assembly, you know that somewhere in here is where the code goes, right, between these sections. So just a quick recap of what the data section is. It just is where you store a bunch of global variables that you can name and initialize at the same time, at the very top. Globals are not great, but sometimes you want to do that in assembly, depending. It's better if you stick all your variables on the stack, like if they're a local variable. It's a little bit better. Think of higher level languages. You typically want to avoid global variables if you can possibly avoid them, and make everything else a local variable or a member variable. So that means somewhere else other than data, probably the stack, but or the heap. Anyway, this is like the basic pattern. We'll say, my variable, and then we'll decide to say what data size it is. In this case, it's dB for 1 byte of data. You could put I think DD in there, or a DW for a word. Sorry, DW would be for a word, and then I think DD would be a double, and then DQ would definitely be a quad word. So here, quad word is 8 bytes. And then I can sort of initialize it to some number, and now I have a global variable. So not like a huge deal. The BSS section is basically where you have uninitialized variables, but you can make huge amounts of variables. You can make an array of variables. So if I say my array, something like that, I could put resource Q to say I want the type of one item to be a quad word, so 8 bytes per item, and then I could just say I want 100,000 items or something. And I'll double check that after I stop recording this video and correct it if I'm wrong. It's been a while since I actually typed BSS here. And then in the text section, this is where you put code and functions and things. You typically want to have at least one entry point somewhere. If you want to make this the entry point of your entire program, you'll probably do global main, and then you'll do main, and then this assumes that you use the GCC libraries, and just sort of return from the label sort of makes it a function, assuming you didn't ruin any of the other data. So those are the 3 sections that we can start off looking at: the data section, the BSS section, and the text section. It's important to note that besides marking functions as global so that they're accessible to other segments or other modules, we also mark functions and labels that we would like to access that are in other modules. So if we're using the GCC libraries, we could say something like global printf, and then right away we're able to call the printf function. Or say if you have another function in another module, like a different source code file that's compiled somewhere else, we could say you know, my other function, something like that. Just mark it as global, or sorry, not global, extern. Global is when you have the function in the current module and you want it to be available to other modules. Extern is when the function or label is in another module and it's already been made available to you, but you want your current module to know that it can access it for the purposes of assembling the program. So that means inside of here, we could do something like call. We could say, let's call my other function. That will work if the other function is actually a function with a return statement and it respects the ABI. You know, it pushes registers that it's going to modify if they're callie saved. If it's not another function, maybe we'll say extern my other jump point. So like not a proper function, but just something that you might want to jump to. Then instead of using call, we would use jump, you know, and so forth. So those are the basic sections. Let's see, for the BSS, I definitely talked about token size and count. And then there's resource B, resource W, resource D, resource Q for the different sizes. So basically just take all the different sizes you could put in the regular data section and assume that that could be popped onto the end of RES inside of the BSS section. If you're interested, this is a segments video, not an assembly video. Another segment that we're not showing here in this source code is the actual stack. Probably, I guess the best way that I could show it is, I don't know, by messing around with the stack pointer. We'll increase, RSP, why did I think it was the instruction pointer? We could increase the stack pointer and then decrease the stack pointer. It doesn't really help a whole lot, but in another video, I'm going to talk more in depth about what the stack is and how to use it and such, but just keep in mind that the stack is where local variables are stored, and you can use it in assembly and C++ and other higher level languages. You can even make virtual stacks in any type of program almost to just sort of, you know, have a stack-like structure. But in C++, if you make any local variable, then it's usually going on the stack, and the stack tends to have a fixed size, and so if you sort of put too much data on the stack, you risk a stack overflow, which will crash your program. Besides local variables, the stack will hold other information that the current scope needs, like its return address. So when we make a function and then let's say we call another function inside of it, actually just up here even, when we call another function on line 22, the stack will receive the return address of where we currently are, so that later when we return from the other function, you know, the program knows where to jump back and forth. It's actually under the hood just jump instructions. When you do call, it's not like a special thing. It's just jumping to another location and then pushing the return address on the call stack. So that's other stuff that the stack holds, which means if you have like an endless or like a infinite recursion happening in your function where just a function calls itself over and over and over again, or you have some complicated call graph and you end up calling too many functions without ever returning, you could overflow the stack. So that's not good. Let me show you a quick example that I'm going to make for you real fast. Oh shoot, did I actually make this? Shoot, where is the, it's on the desktop? Okay, I guess I'm going to make more on the desktop. Let's do a stack overflow. Let me do desktop here. Let's do stack overflow.cpp. I'm just going to make a quick program in C++ that doesn't really do anything except overflow the stack. So I just want you to know the stack can overflow. I'll make a function called f, and f just calls itself. So that's going to be an infinite recursion. And that means, you know, every single time f calls itself, the return address of like line 5 is going to get pushed onto the stack again. So it's just going to get pushed and pushed and pushed and pushed. The stack will overflow faster if I had local variables, because every scope that gets called, even if it's the same function name, it'll have its own allocation on the stack. So if I just sort of like call this from main, and then I'll just need to make a little make file that just kind of compiles I don't really even need to make a makefile. I could do a build script, but I'm going to do it anyway. We'll say G++ standard equals C++ 23, show all warnings, show pedantic. The input file will be stack overflow CPP, and then the output file will be main. And then assuming that succeeds, I'll just run main. So this is like not a makefile video. I have other videos for makefiles. Let's see. Let me get to the desktop. If I run the makefile with just the word make, you should see a stack overflow. We should also see a warning about the fact that there's infinite recursion. Right. No, we didn't see a warning. That's funny. I must have done something wrong or different, because on a different computer not too long ago, I did the same thing and I saw a warning. Okay. Well, thanks for not warning me. But anyway, you can see that we have a segmentation fault here because the stack overflowed. We just made a stack that was too huge. This is a reminder that the stack is not necessarily as dynamic as the heap. You can definitely overflow it. It's not really meant to store gigantic amounts of data. What am I talking about when I say the heap, though? So just keep in mind that whenever you allocate dynamic data, well, maybe, well, what do you think? Maybe instead of calling F, let's call G. The heap is where you allocate dynamic data. So anytime you use the malloc operator in C or the new allocator in C++, you're creating like a dynamic allocation of data. I'll do a new integer, and then I'll do like 1,000 integers. So this is basically going to allocate 1,000 new integers in the heap, which is a segment that is right up against the stack. I should mention also that the stack is important. The stack, its memory locations go down as the stack grows. Keep that in mind, because typically when you imagine a stack, I'll make more videos in the future so you can visualize the stack better. But most of you who know what a stack is already, you imagine that the stack grows upward visually, right? But in your computer, the memory locations of the stack grow downward. So if I add something to the stack, then the new stack head pointer is actually going to be a lesser address. And the reason for that is the stack and the heap, they grow in the same direction towards the same unallocated space. We'll call that space the unallocated memory space, or the unmapped memory space. And it's just, a segment stack in the heap, and then there's the unallocated space that they grow towards each other. If they ever meet, then your program is out of memory and it'll crash. But the heap actually can be dynamically allocated to store tons of RAM. I'm probably about to crash this computer, so maybe this video won't finish recording. So maybe I'll try to crash this at the very end. I just wanted you to see, let me do this. I'll say while true, we'll just allocate a new integer. This is kind of bad form, because when you allocate, a new variable somewhere, you want to have access to it after the allocation. You would usually send that into a pointer. You'd say like, integer pointer p equals new int, something like that, right? But in this case, I don't really care. I'm not going to deallocate that memory. I just want you to see how fast the memory can grow. When we did the stack overflow, seemed like the program died pretty quickly. But here, we're going to be able to see the memory boom pretty big before the whole computer just starts to fall to its knees. So I'm going to do a call to G here, and then I won't actually run this until I'm ready to crash this whole video. Let's see, what else can I say? The reason that the heap can grow so much larger than the stack is our programs now in the modern era, they use virtual memory. So it's not like when we allocate, let's say we're accessing a memory location via a pointer inside of our program. It's not that the pointer has the absolute memory location through the whole system. Like it's not able to name locations outside of the current program. Every program sees its own start memory location as just 0. And then under the hood, there are some extra tricks so that when you try to access a memory location, let's say memory location 100, because you've made, I don't know, this many integers or whatever. Then under the hood, the computer will know what is the start offset of the program's memory. So maybe the start offset is 1000. It's like totally unrealistic, but just pretend the start offset is 1000. Then that means if it's trying to access a pointer with memory location 100, it just gets added to the offset, the virtual offset. So it'll be 1000, and 100 is the real, physical memory location. Or at least at that point, it'll probably go to the paging system, but that's another video. So just know that it's virtual, which means the program thinks it has the full range of the 64-bit memory address space, even if you don't even have that much memory on your computer, which there's no way. There's no way you have so much memory that it's going to overflow or even meet 64 bits at all. But the program thinks it can, so it's just going to grow and grow and grow until you actually run out of physical memory, and then eventually probably your program is going to start going to the page file or to the swap file. And then when you run out of that, then your whole computer probably is going to start crashing. To be honest, it'll probably start crashing as soon as it hits the swap file, because at that point, none of the other programs really have enough leftover memory to breathe, to do extra allocations and things. So everything's going to start slowing down. It's going to be pretty bad. And well, I think that's all I really needed to say. This is not supposed to be a really long video. Let me show you this crasher. I'm going to say goodbye now. Thank you so much for watching the video. I hope you learned a little bit and had some fun too. And that way I've already said goodbye in case the program crashes. We'll see if it actually crashes the computer. So I'm going to open up this, and then I'm going to do maybe htop so that I can see memory. So if you kind of like look at htop real fast, this is just a Linux command line tool that you can install. It's pretty cool. What the heck's going on here? Oh, that's my recorder. You can see here's the memory allocation. So I'm using 2 gigs of 8 gigs on this virtual machine, and then I'm not using any swap space, which means I have not exhausted all my memory, and I have not been forced to go to the disk for like additional memory. But in a second, we'll see that will probably change. So I'm going to do make just to run that. It looks like it's stuck, but if you keep looking at the memory allocation, oh, it already hit 8 gigs. Now it's into the swap already. Probably. Okay, I forgot about that. The out of memory killer, the OOM, successfully killed the program, thank goodness, or the whole computer would have been down. I always forget that that's going to happen lately. But you can see it spiked, right? It went right up to the full physical memory allocation of 7.75 gigs, and then the swap file went all the way up to 2 gigs. You can see that the swap file still has about 700 megs inside of it. That just means that there's memory that isn't really being accessed, so the operating system doesn't feel like it's necessary to pull it back out of swap and put it into RAM. But I wonder if the video skipped when I did that, or stuttered or anything. I'm interested to find out now. Okay, so that's the end of this video. I hope you have a decent basic understanding of segments, and then like the segments and their purpose. The heap and the stack, they grow together. The heap can dynamically allocate to grow bigger. Notice how it went up to 8 gigs just now, basically. Whereas the stack will crash a lot faster. If the stack and the heap meet, then you've ran out of memory. At that point, you probably want to like resize the heap, or the stack just crashes. And then we got the text section of the program, and the data section, and the BSS section of the program. And these sections are a little bit less relevant in the modern era because we have virtual memory and stuff. But when you see a segmentation fault, that definitely means you have tried to access outside of your segment, and it's a no-go. Okay, thank you for watching this video. I will see you at a later date and time. Hey everybody, thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.